Hi everyone, in this video I'm continuing to work through question 13 part C of the 2020 North Sydney Boys Extension 2 trial exam. So I'm still working through part 2 of this 4-part question. Part 2 wants us to work out the sum of the area of the shaded region, where that region is made up of rectangles sitting beneath the curve, and we've gotten those rectangles by dividing the range into n equal parts. Now, in prior videos to this, I've worked through the case where n is an even number, and we did that by first looking at n is equal to 4 and then generalizing. Now we're in the case where n will be an odd number. In the video immediately prior to this, I looked at the case where n is equal to 5, and now what we want to do in this video is try and generalize what we saw to any odd number. So yeah, let's take a look. So I've got my curve, which you remember is the square root of x bracket 2 minus x. That's the function we're dealing with. We've just in the prior video taken a look at n is equal to 5. So let's have a look. Let's examine what's going on here. Now, just like in the other cases, our first two rectangles are flat, like they have no height, so we effectively ignore them. And the key thing here is we don't split the range down the middle, so we're always going to have a rectangle that kind of straddles this point 1, and then we're basically then going to get the remaining rectangles that sit underneath. So I think in terms of thinking about that in generic terms, we can almost put a point here and here, or maybe I'll use another color. Let's use black for our rectangles. And so we know we're always going to have this central rectangle that straddles the midpoint of the range. And then we'll have, I'll just put a dot, dot, dot to kind of say that pattern continues. Just like before, our very first and our very last rectangle won't have any height. And then we'll get a rectangle at this point. And then we'd come up again at this point, so these would connect to make a rectangle, as would this would connect with the line it hits next, and same deal here. And then these connect to form a rectangle, and same here. Again, these should be symmetrical, but at no point have I drawn a good symmetrical semicircle. I guess the key point to note is, well, this will be, well, if our width here is, again, it's 2 on n in generic terms, it's just that n is an odd number now. So this would be the function at 2 on n. This height would be the function at 4 on n. Now, it's worth noting, if this midpoint is n on n, then this would be the function at n minus 1 on n, and this would be the function at n plus 1 on n. And then as it was in the other cases, this is 2n on n, so this would be the function at 2n minus 1 on n. And so as we have in all the prior cases, we're just kind of putting this all together to get our result for our area. So in this case, the area will be, well, if I just kind of shade what we're dealing with, it's kind of all of this. So it's going to be the width, which all these rectangles will have a width of 2 on n, times the value of the function at 2 on n, since that's the height of the rectangle, and then plus 2 on n times the function at 4 on n. And so on. And then we're going to have, well, this rectangle, kind of like what we saw in the case where n is equal to 5, you can kind of pick one of these. You don't need both because they both form part of the same rectangle, this central rectangle. So in theory, we could just pick one of these, but kind of like what we did when we were doing the general case for n is equal to odd, it's helpful if we can keep writing things in a continual summation so that we can use our sigma notation. So what I'm going to do is I am going to write both, and then subtract 1 off the end to kind of even it out. So we're going to say 2 on n times f of, in this case, n minus 1 on n, plus 2 on n times f of n plus 1 on n, plus, and so on, all the way up to our last one, 2 on n f of 2n minus 1 on n. And that kind of deals with everything, except because we've effectively counted this when we didn't need to, I'm going to then subtract that off the end. So minus 2 on n f of n plus 1 on n. Alright, so just like we did in the even case, which I'll just flick back to remind you, so we want to kind of take the main part and put it into sigma notation and then just have this extra bit subtracted off, and then we simplify. So let's do the same thing. Let's take this main part, which kind of gets up to here. So everything's got a 2 on n in front of it. So we're going to have 2 on n times, and then sigma notation. Once again, we're going from, I'll use r as my variable for consistency, and we're going to go from r is equal to 1 up to n minus 1. And again, in each case, we're doing the function value at 2r on n. So it'll be 2 times 1 on n, 2 times 2 on n, and so on, up to 2 times n minus 1 on n. So that's what's in this sigma. But now the key difference here is we're subtracting off 2 on n, not f n on n, but f n plus 1 on n. Alright, now in terms of how we simplify this, well, if I look at this first bit here, that's essentially, if we flick back to when we were dealing with the even case, 2 on n times the sum from r is equal to 1 to n minus 1 of f2r on n. And then what have we got right now? 2 on n times the sum from r is equal to 1 to n minus 1 of f2r on n. So this bit here, whatever it's simplified to, is going to be the same. So we can really just skip over these steps and know that it's going to get to the same thing, which actually I think we kept going, didn't we? We got to 4 times the sum from r is equal to 1 to n minus 1 on root r n minus r on n squared. So I think we can just skip straight to that. So this is going to be equal to 4 times the sum from r is equal to 1 to n minus 1 of root r n minus r, all divided by n squared. And so now we just really need to think about how this minus 2 on n f n plus 1 on n simplifies. So let's again throw n plus 1 on n into our function. So it's the square root of n plus 1 on n times 2 minus n plus 1 on n. And this might take a bit of work. So that's going to be equal to 4 times the sum from r is equal to 1 to n minus 1 root r n minus r on n squared, minus 2 on n times the square root of, so we've got our n plus 1 on n out here, times, again we'll get a common denominator, so it'll be 2n minus n minus 1 on n. So that's going to be 4 times the sum from r is equal to 1 to n minus 1 of root r n minus r on n squared, minus 2 on n times the square root of, this will be n plus 1, and then this will be 2n minus n is n, so n plus 1 times n minus 1, and the two n's will come together to give n squared. And still probably enough room to write one more line, so 4 times the sum from r is equal to 1 to n minus 1 of the square root of r n minus r on n squared, minus 2 on n. Now n plus 1, n minus 1 is n squared minus 1. So it's the square root of n squared minus 1 on n squared. Now, again, you could leave that and that'll be fine. But anticipating that we're eventually going to use this in a limit as n goes to infinity, it's going to be helpful to kind of clean this up just a little bit to write it as n squared on n squared, or just 1 on minus 1 on n squared, because then when you throw in infinity it's much easier to see how it simplifies. So I might just turn over and write that as finally the area is equal to 4 times the sum from r is equal to 1 to n minus 1 of root r n minus r on n squared minus 2 on n, and this will be the square root of 1 minus 1 on n squared. 1 minus 1 on n squared. And notice that this is essentially, if again I just flick back to our case where n is even, it's essentially the same, except the thing we're subtracting, instead of just minus 2 on n, it's minus 2 on n, 1 minus 1 on n squared. It's that slightly different adjustment, which is why we get different numbers when n is odd. Yeah, just like last time, we can do our check. So let's check when n is equal to 5. If I substitute n is equal to 5 in here, do I get this number? Hopefully I do. If I don't, there's probably been a mistake somewhere. So this is the moment of truth. The area would equal 4 times the sum from r is equal to 1 to 5 minus 1 is 4, times the square root of r, 5 minus r, on 5 squared is 25, minus 2 on 5 times the square root of 1 minus 5 squared, which is 1, 5 squared, 1 on 25. So that's going to be 4 times square root of 1 times 4, and I'll bring out this 25 again so I don't have to keep writing it, plus the square root of 2 times 3, plus the square root of 3 times 2, plus the square root of 4 times 5 minus 4 is 1, minus 2 on 5 times the square root of 1 minus 1 on 25. And what I might do now is just simplify all these square roots. So it's, what is it, root 4 is 2, plus root 6, plus root 6, plus another 2, minus 2 on 5 times the, what's 1 minus 1 on 25? 1 minus 1 on 25, oh yeah, I should know that, that's just 24 on 25. And I might just start keying this into my calculator, because that's what I did for n is equal to 5. I didn't try and simplify it in any rational form. So let's just do this bit here. So it's 2 plus the square root of 6 plus, 2 plus the square root of 6 plus the square root of 6 plus 2 times 4 on 25 minus 2 on 5 times the square root of, I might delete that, times the square root of 24 divided by the square root of 25, which is just 5. So let's write that out. 1.031918359. Now let's just flick back and see, is that what we got when we worked out n is equal to 5 manually? 1.031918359. 1.03191, yes, perfect. So you can see that just demonstrates how when n is odd, we do indeed have a different result in general to when n is even. So we did have to work through both of these cases. So if we now kind of assess everything we had to do to be complete for this part 2, which again, remember, was worth 2 marks. We had to, I mean, technically we didn't have to check for n is equal to 4 and n is equal to 5. It was helpful, but technically it's just this n is equal to even, doing all this work, and then we're able to check because we did the extra effort. And then again, n is equal to 5 is just extra help for our checking, but then n is odd, all of this work, and then the check. I mean, seems to me like a lot of work for 2 marks, especially when you compare just how little work we had to do in part 1 for, where are we? All the way back in part 1, this is what we had to do for 1 mark. And compare that with what we had to do for 2 marks. I just wonder whether the person who wrote this question didn't realise just how much was involved. I mean, any student who managed to get through all of this in the context of a timed exam where this is just one little question in a very big exam, this is question 13 part C, and there's more to come in the exam. So yeah, pretty rough, I got to say, in terms of yeah, the amount of stuff that's being asked of students in this exam. Quite rough, and that's assuming you can even work out what's going on. I mean, I can imagine many students can't even work this out, let alone have enough time to show it all in a kind of complete and rigorous manner. So anyway, that's just a little side rant from me. I just don't think this is particularly fair in terms of the context of an exam. But hopefully, in any case, you've been able to follow along with all that, because even though it might not be the fairest exam question, it is a very interesting question. And the techniques we're using are actually quite similar to some other tough Extension 2 questions I've encountered. And maybe at some point in this journey I'll provide some links to some of those other questions, because they are quite interesting. And I think this is a technique that you definitely need to be across in preparing for the final HSC exam, because it is something that does come up often enough that you'd want to be prepared for it. So hopefully that's all made sense so far. Now we're going to move on to part 3 of this question. All right, tick boom.